In the world of chemistry, chemical reactions are classified based on the course you take in some cases. For the most part, there are really just two classifications of chemical reaction. Oxidation reduction and metathesis reactions. And when we get to them, I will define them in more detail. But I just want to class out these reactions. Now, this is the classifications we'll use in this course. But if you go to organic chemistry, you'll find a classification of reactions which come together like this. And what makes this note useful to you is I've created an acronym that you can take to the future if you do take organic chemistry, and hopefully this will pop into your mind when you do take the course. SEAR, like Sears and Roebuck. Makes it the classes of reactions are a little more memorable. S stands for substitution, where one item replaces another in a molecule. Elimination, reactions, and as a result something falls off a molecule for whatever reasons are present. Addition reactions, in which a new part hooks onto a molecule, and rearrangement reactions. Rearrangements occur to achieve a more stable condition for the molecule. So parts of the molecule may shift to a different carbon or something of that nature. Now, we're not getting into this, but what I wanted to emphasize is that depending on the course you're taking, you may run into some different classifications of reactions. But regardless of what you do, reactions are essentially reactants going to products, no matter what. But the classifications give you more of an indication of the mechanics of that reaction. Oxidation reduction reactions are reactions which undergo changes in oxidation states of their constituent elements. A good example of the or classes of oxidation reductions include decompositions, and composition reactions, and what we call single replacement reactions. In your outline on reactions, you can see up here, at the bottom have the decomposition list, and the reverse of these is composition reactions. So these are your primary reactions you need to study and learn, memorize, and so forth to apply in the future. And these will be very easy to remember if you practice on them, because I built an acronym that can help you remember them. COACHE, Coach E. So now I'll just go through a couple of these, but you need to practice these, and I'll show you how to put them together. They're very straightforward. So in your outline, again, the listing is COACHE. So the character of decomposition and composition is that the outcome produced winds up with less than you started with. That's one general characteristic of decomp. On the other hand, composition, you start out with more than you wind up with. Decomp, you wind up with more than you start out with. These refer to carbonates, which are derivatives of the CO3 2- ion. And then you have oxides, IDEs, meaning by themselves, oxides of metals. So you would have iron, say, iron plus O2 going to FeO, and then you'd have to balance this, something like this, where you'd have iron 3, so you would have 2 irons, and you'd have to balance your oxygen, so let's do it a 3 and a 2 and a 4. There we go. That balances it out. Like that. Acids. Generally polyion acids. You recall yesterday we talked about polyions end in ATE endings and ITE endings. If it ends in an ATE, your acid will be an ic acid, like sulfuric acid, nitric acid, phosphoric. If it ends in an ITE, it becomes OS acid, sulfurous acid, nitrous acid, and stuff like that. But acids are very labile. Labile meaning unstable in the presence of heat. So acids like H2SO4, and if you heat it, it'll go to SO3 plus, let's see, H2O. Let's see what that balances. 3, 4, 1 sulfur, a couple hydrogen, yeah. So it breaks down into stuff like this, and this is a gas out of the system. Chlorates. And this is a ClO3-. This is also proportional to what we call an analogous series. And that means, while you have other halogens like chlorine here, you can apply the same thing to bromine, and that's bromates. Or iodates. And of course, the entire collection will apply as an analogous series. But potassium chlorate, for example, you heat it and break it down, it leaves a smoke trail, looks like a space shuttle taking off. So anyway, hydroxides, OH compounds, calcium hydroxide and sodium hydroxide. Group 1 or group 2 hydroxides heated will break down into metallic oxide like calcium oxide and water. You can read these on there just as easy as I can. But you need to sit down and practice and play with it. I can't work them all out. Now this is the only one that is not a reaction in the context of what I've shown you so far. This is called electrolysis. This is a salt plus an electric current. Gives decomp products. And we're going to talk about that in just 1 second, right now, as a matter of fact. And the type of chemical reactions and equations that we have to write. So when you are talking about these kinds of structures, you're talking about decompositions. Now, KClO3 is a solid, and we're going to heat that, and according to the list here, it's going to break down into potassium chloride salt and oxygen. It's going to give off. Going to go to KCl as a solid, and O2 as a gas. And there's a couple things I want to show you in here that about writing equations, and some of you know, some of you do not know about these. We'll take a break in a second too. Balancing this out, we need a 2 here, a 2 there, and a 3 there. Okay. When writing molecular formulas, and equations, substances must be in, this is the new term to some of you, basic, standard, state. The term basic standard state is a critically important term and expression for your understanding in chemistry. Basic standard state of substances is the most common form of a given substance. And you have in this substance world 2 areas. Substance, as you recall, are divided into elements and compounds, or molecules. Let's put molecules, that'll mean more. Elements in basic standard state. How do you know what an element is in basic standard state? Now, what we're asking here is, what is the formula of an element in basic standard state? What is the formula for molecules in basic standard state? Well, to determine that, you need to use what we call a thermodynamic quantities of substance, a thermodynamic properties table. Basic standard states substances, or standard state substances, are defined by what we call a heat of formation. And is given by this symbol delta H subscript F with a superscript circle. The superscript circle refers to standard thermodynamic conditions, which are 25 degrees Celsius and 1 atmosphere. That's thermodynamic. Now, This is the beginning of a thermodynamic properties table right here. In ebbing thermodynamic quantities for substances and ions at 25 degrees right here. And you'll notice in this it has a delta H, delta G, and S. Those are thermodynamic property symbologies. We'll learn about in more detail when you get into Chem 2. But this is what we're talking about right now. It's a heat of formation, delta HF, designated in units of kilojoules per mole. And by definition, delta HF is the heat gained or lost on formation of a substance from its basic elements in their standard state. Okay, this is a page out of the thermodynamics table. And I'll zoom it in just a little. So what we're looking for is the delta HF numbers that go with each of the substances listed over here. Okay, so in a reaction, you might need an element. Okay, what form do you write that? So remember, what I'm trying to teach you here is why do we write the formulas of elements in a certain way? Why do we always use O2 or Cl2 or I2 or N2 and so forth? Well, it's because it's a basic standard state. To determine a basic standard state, say you scroll down here and you find a 0. The form is Br2. So if you're going to put Br2 in a formula, an equation, bromine in an equation, you need to put it in the form of Br2L, liquid form. That is your basic standard state. Or if you're using calcium, you scroll down, there's a 0 right there. And so you have all of these that will demonstrate that. The basic standard state of carbon is graphite. And so this is why we use those. And when we talk about compounds that are not elements, they do not equal 0. For example, if I'm looking at calcium chloride, notice the delta H number here is a minus 795.8. So compounds, there's only one of those. But elements, you have several. Going back to bromine, you see we've got different forms of bromine that could be used, but only one in here is your basic standard state. So that's what I'm trying to teach you, how to write equations in the proper format. Now, that doesn't mean you can't write it in other formats, in ionic equations, in net ionics, and so forth like that. So when you write a chemical equation, the molecular equations are always in basic standard state. And so if I were to, again, write the potassium chlorate, I would look up and find the form of potassium chlorate would be this molecule. There wouldn't be any other, so I'd have to use that. And out of this decomposition comes KCl. And there's only one KCl, and that's KCl solid. And it gives off oxygen gas. Well, if I'm going to use oxygen, I'm going to have to use it in O2 form. Now I want to show you something that you may or may not know about the diatomics. How many people know how many diatomic standard states there are? Anybody ever see this little trick?
7.
How many?
7.
7, that's exactly right. So I'm going to teach all of you how to remember that very quickly. on the periodic chart, block off nitrogen, oxygen, and the halogens down to iodide, and look at the shape of that number. You just have to remember hydrogen. H2 is also included, but you see that's 7. And those are the 7 elements that you would put into basic standard state if you were writing a molecular equation. So that's just kind of a little trick that I learned years ago that if you were playing around, but no other element in the collection of elements. Now, all elements in basic standard state have zeros, but if they're not in the basic standard state, they may have a delta H number. Okay, now that's everything you need to know for the short term. Okay, in writing chemical reaction, what I wanted to show you was in the molecular equations, we will write them in certain ways. Like, and these, the way these are couched, of course, still apply to the sum of charges equals 0, but some of them are elements in basic standard state, and we're bound in doing that unless there's a specialty equation that serves a situation. After the decomposition and composition reactions, there's what we call a single displacement reaction. And what this does is it replaces an active metal or an active substance, replaces a less active substance in a compound, and has an empirical formula: A plus Bx goes to Ax plus B. And so A would prefer to hook up with X more so than B, and we'll learn about those bonding preferences as we get into chapter 9 and 10 in the near future. But at any rate, this is the more active metal, and this is the less active metal. Well, how do you know if one's more active than the other? Well, apply activity series. The activity series of elements is a listing of metals from most active to least active. And this table will kind of give you an illustration if you need it. I'm not asking you to memorize this for sure. But what you should know is that in a typical reaction, a single replacement, lithium being up the top of this will replace any element below it, and potassium will replace any element below it in the reaction, but not lithium, and so forth and so on. Like nickel will replace tin, lead, hydrogen, copper, and so forth, but will not replace anything above it in this list. And if necessary, I will attach the list to the exam, and you just pick out what is used. So let's look at some of these equations and define some more terms on oxidation reduction. Okay, so that's like zinc in basic standard state. You don't have to look them up every time. You can assume that these are given in that. Plus copper sulfate in an aqueous medium. And the outcome is that the zinc will replace copper in, oops, I'm sorry. There we go. Zinc will replace copper in this compound. So we want to look and be sure that zinc is above copper in the activity series. So we find zinc right here in this series, and way below it is copper. So our reaction will proceed to give zinc sulfate and copper. Now, when we started with a basic standard state element, and what happens is when you kick out the copper, it goes to a basic standard state also. All of them do this. Zinc then becomes a +2 charge to match zinc from the fixed charge elements on your periodic chart. If you look, it's one of the fixed charge +2 elements. Okay, so we've written the reaction products out of this. Now check the balance. There's a 1 to 1, and when balancing, balanced by polyion groups, and makes it a little bit easier. Now, when you look at this sulfate's a -2, copper's a +2 given in this. So we have the oxidation states. This is 0 and copper 0 in there. So if we look at what's happening between the zinc and the reactant side and zinc on the product side, we see that zinc has changed its oxidation state from 0 to +2, while copper has changed its oxidation state from +2 to 0. So if we make these comparisons. Now, the next question is, how did this occur? It occurs by oxidation and reduction. To go from, and as a result of electron transfer. So oxidation reduction deals with the process of electron transfer. Now, in this process, two things are required. You must have balance of charge, and must have balance of mass. Well, many reactions that you are probably familiar with are balanced by inspection, and we assume that you have covered that enough in previous courses that you know the sum of all the masses on the reactant side must equal the sum of all the masses on the product side. So, I mean, that goes without saying. At any rate, but two requirements in any oxidation reduction process are required. You must have a balance of charge as well as a balance of mass. So when we look at this one going from 0 to +2, and electrons are negatively charged, so, and protons being positively charged, you can't lose or gain protons or you change the element. So going from a 0 to a +2, the element zinc becomes more positive. The only way it can do that is have a surplus of protons. That means it lost 2 electrons. Everybody comprehend that? Everybody see what I'm doing? Well, it's going to get tricky here in a minute when we start balancing these things. In this one, in copper, we go from a +2 to a 0. That means we went to a more negative direction. In order to cancel the 2 positive charges, we have to have 2 negative charges. Of course, those are the electrons. So this gains 2 electrons. So in this simple equation, there is a balance of charge. We have 1 zinc, each zinc losing 2 electrons and becoming +2 charge. And then we have a single copper gaining 2 electrons and becoming a neutral element over here in basic standard state. Now, who is who? Who's undergoing oxidation and who's undergoing reduction? Well, there's an easy way to remember it, and again, another one of my acronyms, oil rig, to remember your oxidation reduction. Oxidation is loss of electrons. Reduction is gain of electrons. Oil rig. That couldn't be easy. So if this zinc lost 2 electrons, then that would be an oxidation process. Whereas on the copper, it's a reduction process. Now, in this context, listen to what I'm about to tell you. These are processes. This is gain and loss of electrons by process. Now, in this, we see the oxidation. Another way to write these is what we call half reactions. And oxidation, being loss of electrons, is sometimes written, it's called the oxidation half reaction. See, zinc goes to zinc plus 2 electrons. That's the oxidation half reaction. That's a process. Reduction side of this is copper gaining 2 electrons, and you see it copper plus 2, and usually it's in solution, aqueous solution, but I'm going to put it in here as 2 electrons going to copper basic standard state. Notice where the electrons are located relative to the arrows. So if the electrons are on the right of the arrow, it's an oxidation or it's a loss. Whereas if the electrons are listed on the left of the arrow, it's a gain of electrons or a reduction process. Now those are chemical processes, gains and loss of electrons. But the substances have what we call agent terminology. And the term is opposite whatever the process is. Zinc, while zinc is undergoing oxidation, zinc is a reducing agent. So we have a process of losing electrons by a reducing agent. So don't get that mixed up. The agent is always opposite the process. And copper is an oxidizing agent. Terminology that's widely used and commonly used in the chemical world. Oxidation and reduction terminology. So now one of the rules also for oxidation reduction, in any reaction there's only one oxidation process and one reduction process. One oxidizing agent and one reducing agent. Now sometimes a compound will have an element in there that will, part of it will go to oxidation, part of it will go to reduction. That's called disproportionation. I'll show you an example of that in a few minutes. So what we want to do is now look at the oxidation reduction reactions and understand the process of balancing those reactions. And it requires you to follow oxidation reduction rules. Now you will not have this rule list on test day. So, and I've given you plenty of examples in the handout that I've just given you to develop your skills. Now, you want to begin with this handout right here. And I'm going to work through some pages, and here are the examples we're going to work through. And I can't, obviously, I don't have time to work them all. But we're going to start out and learn to do oxidation reduction as part of your learning curve in Chem 1 at this point, learning how to deal with oxidation and reduction reactions. And there are various ways to balance oxidation reduction. Some people call them oxidation number methods. Some people half reaction methods. Some will use addition of half reactions methods. Okay, so I'm right here. Balance oxidation reduction reactions. Balance each of the following redox reactions as given. Okay, so you may not have it in molecular form. There may be an ionic form, but still you can identify the oxidation, reduction, and balance the equation relative to what you're looking at. And you will need to do that. So we're going to start with, in short, these go redox reactions. So our first one is we'll have oxygen in the -2 format, and then we have basic standard state of fluoride going to basic standard state of oxygen and fluoride ion, like this. That's easy enough to throw a 2 and 2 in there, but have you really balanced it by both the mass and charge? Well, step 1 in the balancing of oxidation reduction reactions is assign oxidation numbers. This is step 1. Now here are your rules for assigning oxidation numbers, but I don't go over those in great detail because it takes too much time we don't have. As I go through balancing a few equations, you'll begin to see those, how these things are done. Just remember, oxygen and hydrogen are -2 for oxygen, +1 unless I tell you different. And I'll show you those if we, I don't see it. Yeah, I see number 8 in that page has oxygen as a -1, and that's one of the uniques. Okay. So first thing is -2. Well, if you have element and basic standard states, all basic standard states have oxidation states in the 0 state. Oxygen be 0 right here, and fluoride, that is a -1. And this one, put a -2 over here. I'll put it in parentheses just for emphasis. Okay, once you assign those, then what does it say? It says determine change per atom. Change per atom. Okay, so oxygen is going from a -2 oxidation state to a 0 oxidation state, while fluorine going to fluoride, 0 to a -1. Okay, so we've assigned oxidation numbers, and then we identified per element. So what this is telling you is I have an oxygen atom going to an oxygen neutral in the process of going from -2 to 0. Well, what does that mean? It went to a more positive. So in this case, it lost 2 electrons right there. Fluoride, going from a 0 to a -1, gained 1 electron. Like that. So far, so good? Yes, sir.
Wouldn't it be the opposite way?
So as it loses 2 electrons, this is per element. This is the way I want you to think about this, because when if you've not got any experience with this, or very little, you need to think a certain way in order to deal with some of the more complex systems. Now, what you cannot ignore is the subscript over here. O2 is O2. And as that, remember what I told you about subscripts. Once you put that subscript in, it's locked, because it's the number of elements in that compound. So I have to have that going on both sides. So I will balance it with a 2 right there. But I also are now saying, now watch this. I have not just 1 losing 2 electrons, I have 2 oxygens losing electrons. so that I have two, each losing 2 or 4 electrons undergoing transfer. Now, those don't just disappear. They are gained by something else. So now we look at fluoride. One fluoride will gain an electron, but I have to have 2 over here. I have to have enough fluorides over here to gain all 4 electrons. See, one fluoride will gain 1 electron. So I have to have 4 fluorides gaining 1 electron, and I'll have a 4 over here. Now, see, you can't ignore the issue that confuses students frequently is the subscript. You cannot ignore it, and you have to say, okay, I started with 1 element changing. What do I have to do over here to balance with this one over here? Well, to balance these, you'd have to put a 2 here. You can't just throw away the 2. And so that brings 4 electrons here. So when you compare these two, 4 electrons lost equal 4 electrons gained. So that's balanced relative to charge and mass. Same way with this next one, where you see aluminum in basic standard state plus O2 going to oxygen minus 2 plus aluminum plus 3. Okay, first thing we need to do is assign oxidation number. Well, if it comes to you like this, it's automatically assumed to be 0 charge. Oxygen O2 is basic standard state of oxygen, so we assign an O to that, minus 2 on the product side oxygen, and a plus 3 on the aluminum. Okay, then we see what the changes per element are. So aluminum, we see, is going from a 0 to a plus 3, and oxygen is going from a 0 to a minus 2 per oxygen. So how did these occur? Well, 0 to minus 2, well, this one would have to gain 2 electrons right here, whereas aluminum would have to go to a more positive direction. So the only way to do that is to lose electrons. You have a deficiency of electrons now. So you lost 3 electrons right there. Now notice it's 2 electrons right there. So you have an unbalance here. But first you have to balance the oxygens, and then of course the aluminums. Aluminum's 1 and 1 anyway. But since I have a 2 here, I have to have 2 here. That means the 2 has to go in here. 2 oxygens each gaining 2 electrons, and so I have 4 electron total here. So I'm going to bracket that. I know it's getting messy right in here, but there's 4 electrons, there's 3 electrons. I have 1 aluminum losing 3 electrons. Now I've got to balance those 2. So what I'll do is I'll just bring a 3 up here and a 4 down here, so that I have 3 aluminums. Four aluminums. Each of those 4s losing 3 electrons. So I'll need a 4 over here. So you have to think like that to understand these kind of balance procedures. Here we have 3 to 4 is 12, so I have 6 oxygens, each gaining 2 electrons. 2 to 6 is 12, and so I have to increase this to 6. 2 times 3 gives you that 6 there now. So you have to think in terms of starting individual elements and then multiply them up as you go along, based on the subscripts as you are getting. Here we have a potassium plus a zinc going to neutral zinc plus potassium. Assigning oxidation numbers first. Here we go. Then we look at what's going on here. 0 to plus 1, and then plus 2 to 0. Well, we don't have any subscripts to deal with, so it should be easier. So 0 to plus 1 is lost 1 electron, and this one gained, I'll put it under here, 2 electrons on this one, right here. So now I get to balance the two that are the charge. So if I have 1 zinc gaining 2 electrons, I have to get those 2 electrons from somewhere, so I have to have 2 potassiums gaining those, delivering those electrons. So you see how you make choices as to how many elements you need to achieve the charge balance that way, and it's balanced by mass, just looking at it. Okay. Now you go down here to number 4, you have chrome, dichromate ion, going to just the chrome. And these are half reactions. Chrome 3. So what we want to do is insert either an oxidation or a reduction based upon the change we identify here. So for this half reaction, we're either going to place the electrons on the left of the arrow or after the chrome over here on the right of the arrow, depending on what the transfer indicates. So, minus 2 overall. Okay. Now, I told you, unless I tell you different, oxygen's always minus 2. So it's still a minus 2 in here. Then I put a blank over the top, and it's a minus 14. Now I have to add 14 to something over here to get a net minus 2. So what would this be? This would be a plus 12. So plus 12 minus 14 gives me a minus 2. Everybody see what I did? All right. So I have 2 of them, so each one of the chromes is a plus 6. Everybody good? Any questions? Now, identify what's going on here. Since it's a half reaction, it's either going to be oxidation or reduction. So you have 2 chromes going over here, one for 6 to plus 3. So 6 to 3, that's gained 3 electrons in here. But you can't ignore the fact that you have 2 chromes over here. Okay, each chrome gained 3, but it says you have 2, so you have to account for those 2. And therefore you increase the product side over here. And what you would do is you put your 6 electrons on this side. That is the gain of electrons. Now, if you go on down that list, you want to balance your oxygens. If it's in acid system, you would put 7 H2Os. You read the rule on down the list, whatever I did with it. Balance oxygen, you can see down here, 8A, add water to the side needing oxygen, and add H pluses to the side needing H pluses if you need any. So that would be 14 H pluses. And I sometimes put them over the arrows. And so that's balanced half reaction in an acidic medium. Okay, so we have an H2 O2, and that's plus dichromate. And that's going to oxy plus chrome 3. That over a little bit. Like that. So what do we do first? Now here's the oxygen that is -1. It's one of the few, and I'll make a note on the test or anything like that. I don't make a note, you just assume it's -2. So the net is -2. So hydrogen's +1 and +2 net. So you add these together, you get 0. And so there's your oxidation states per element as well as the total. And this one again is -2, -14, +12, +6, and the net is -2. I'll just do that to show that. And oxygen 0, and chrome is the +3, like that. Everybody good so far? I'm doing this? So that's what I say. I don't need to go through all the rules of oxidation, because the sum of charges of the dichromate's got to be -2, so you got to figure out what each one is. Now, the first bracket has to deal with what? Per element change. Then you scale up by the subscript. So here we're going from a -1 to a 0. And then we're seeing the chrome going from a +6 to a +3. Okay. Now I've gone through a few of them. You should be able to make decisions now on who's doing what. -1 to 0 is more positive direction. That means you've lost 1 electron per element, per oxygen. And +6 to +3, that cancels out 3 of the positive charges. So we're looking at gaining 3 electrons in there. And so in the formulas that we have, we cannot ignore now the subscripts. That was per element. Now the multiples. So we have to take into account that 2 oxygens are each losing 1 electron. You catching on? And so over here we already have a 2 for the subscript, so we don't have to do anything. And the chrome, we have 2 chromes, each gaining 3 electrons. So I have to put a 2 here. That means I have 6 total chromes. Well, excuse me, 2, 3, 6. So each one's gaining 3. I have to have the 2 over here. That's right. So I have 2 chromes, each gaining 3 electrons. Well, we already have the subscript in there to accommodate that too. So there's a balance of whatever's going to go oxidation and reduction. Now let's move down the rule list here. Look at the rules. Balance the total charge. Balance elements undergoing charge transfer other than oxygen. We don't have anything in there that's not undergoing oxidation reduction. So we move on to balance the oxygens. And the instruction says this is an acidic medium. So to the side needing oxygen, you add 1 water per oxygen needed. So when we look at this, how many oxygens do we have over here on the reactant side? And we have 2 oxys on the product side. So I need to add 5 waters on this side. Everybody follow my little trick there? I'm just following the rules here. And to the side needing hydrogen, so we got 2 hydrogens over here, 10, so I need 8 H pluses. And that balances that reaction by the oxidation number method. So that we look at 8 and 2 is 10 hydrogens. We'll do the accounting on it. 8, 9, 10 hydrogens. 7, 8, 9 oxys. Over here, well, we missing somebody? No, 5, 6. I got 5 and 2 is 7. Did I miss one somewhere? If I had a brain, that'd be dangerous. Okay, we take tellurium plus the nitrate ion, and we're in a basic solution. Goes to tellurium oxide. And into O4. We go through this. Now, balancing at the basic, balancing oxygen and hydrogen is where students get confused, so you want to concentrate on this. Everything up to that point, balancing until we get to the oxygen hydrogen is the same as what we've already done. So we put the oxidation numbers in. So this is a -2, -6, and so that'd be a +5 for the nitrogen, and that's a -1 overall for that one. Put tellurium, I'm running out of space, I'm going to spread this out. And let's see, what's the other one? Into O4. There we go. Okay, oxygen is a -2, -6, so that would have to be a +6. Oh, not true. -2 overall, so that would be a +4. +4 -6 gives me a -2. And this is -2, -8. So I have to have a neutral +8. What am I doing? +8. And 2 to 4 is +4. So nitrogen has gone to a +4. That's what I was telling you earlier. Once they get into compounds, they don't necessarily conform to the periodic table. So now we need to identify the changes. Per element. Everybody good? Stop me if you need to. 0 to +4 means we've lost 4 electrons per element per tellurium. And 5 to 4 looks like we've gained 1 electron per nitrogen. Well, this nitrogen on the right side is showing a subscript of 2, so that means we must have 2 nitrogens over here. On the reactant side, each gaining 1 electron, going over here, so we have 2 electrons involved here. And tellurium is each element lost 4 electrons. Well, that doesn't balance here, so what I need to do is I need another 2 nitrogens in this case, so that would make this into a 4, and I put a 2 right there. So now I have 4 electrons gained and 4 electrons lost, so those are 1 and 1, so those are as is. So now we need to balance the oxygens in here, and what does it say? To the side needing oxygens, you add 2 hydroxides for every oxygen needed to the side needing oxygen, and the other side half as much water. Okay. And then you turn around and reverse that in the hydrogen addition. For basics. See if you can interpret this. 2OH slash H2O, then H2O slash OH minus. That's what that rule is. OH, H2O, H2O, OH, but you start out with two OHs. And what this says, to the side needing oxygen, you add 2 hydroxides for every oxygen needed to that side, and half as much to the other side in the form of water. See what I did? Then this balances the oxy balance. This balances the hydrogen if you have to balance it. To the side needing hydrogen, you add 1 water for every hydrogen needed, and to the opposite side, the same amount of hydroxides. And then you simplify, because you'll have OHs and on the right side and OHs on the left side, and they'll cancel out like an algebra equation. So let's see how this comes together. Might need to rewrite it, but we'll look at it. All right, on the left side, we have 3 times 4. We have 12 oxys up here. And on the right side, we have 8 oxys. So we need 4 oxy on the product side. But the rule says add 2 hydroxides per oxy needed. So if I need 4, I need to add 8 hydroxides to the product side. Yeah.
Aren't there an additional 3 oxygens in the...
Let's see, I got 8. Oh, I forgot those other 3, didn't I? 2, 4, 8, 9, 10, 11 oxys. My bad. 11 oxys. Thank you, sir. So in this case, we just need 1 oxy. So we add 2 hydroxides. Thank you, sir. Keep me honest, guys. So I need to add 2 hydroxides. So I'm going to come up here and add 2 hydroxides to this side. Everybody still on with me? A little bit? Okay. And to the opposite side, half as much water. So I'll come over here and just put 1 water. Everybody still in? So that takes care of this rule right here. Now, check the hydrogens. We got 2 hydrogens and 2 hydrogens. So that's your balanced equation. So I'll try to write the working equation now. Always, it gets so messy while you're trying to balance it. Hard to see what anything is happening. Now, on test day, one of the answers they'll ask you for, when balanced, what's the sum of all the coefficients? When balanced, add up all the coefficients, and they'll have the list A, B, C, D of that addition. So here is 1 plus 1 plus 4 plus 1 plus 2 plus 2. 2, 4, 5, 6, 7, 8, 9, 10, 11. So the sum of your coefficients is 11. So that's just warning you about the type of questions that could possibly show up. Not just balance it, but you have to take the coefficients and remember to add in the ones that constitute those with coefficients of 1, like that.